Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here with us today. We're taking a super fascinating look up at the sky to decode the hidden mechanics behind our daily weather changes. If you've ever wanted to predict your own local weather better than the meteorologist on your evening broadcast, well, you are in the exact right place. We're going to break down the massive, invisible physical forces that are literally colliding above our heads every single day, and we're going to turn those abstract weather maps into completely clear, actionable science. So, picture this. It's a scenario we've all experienced, right? You step outside in the morning, the sky is beautifully clear, and the air is perfectly calm. But fast forward a few hours, and suddenly the temperature absolutely plummets, the wind is howling, and you're caught in a violent thunderstorm. Why does that actually happen? It can often feel like total atmospheric chaos out there. But the truth is, it's not random at all. Actually, there's a highly precise, structured sequence of thermodynamic events happening up there. And once you know what to look for, you will literally never look at the sky the same way again.
Okay, let's dive into this. Today we'll be laying out our structural roadmap to solve this atmospheric puzzle by covering the rules of the air, how clouds are born, the aggressive cold front, the gradual warm front, and finally, a head-to-head comparison.
Kicking things off with Section 1, the rules of the air, where we are establishing the indisputable laws of physics.
Now, before we can truly appreciate the mechanics of these massive storms, we've got to do a quick refresher on the absolute foundational laws of physics that govern atmospheric buoyancy. These properties dictate literally everything we're about to explore, so we need to lock these in. First up, we have warm air. Because it has a smaller density, it's really buoyant. It naturally just wants to rise up. On the flip side, we have cold air. Cold air is significantly denser, it's tightly packed, and it is highly prone to dropping or sinking. So here is the absolute, indisputable rule of the game. If a massive cold air meets a massive warm air, the denser cold air will always force its way underneath. Always. The warmer air simply doesn't have the heavy kinetic weight to push that dense, cold barrier out of its way.
Moving right along to Section 2, how clouds are born, focusing on the journey of moisture.
So the crucial point is this direct cause and effect relationship between temperature changes, air pressure, and water vapor. You see, warm air has a massive carrying capacity for moisture. To put that scale into perspective for you, just a single rising column of humid summer air can hold millions of gallons of invisible water vapor. Millions! But as these little packages of damp air rise higher into the troposphere, the atmospheric pressure drops. This causes them to expand and cool down. And once they hit this really specific threshold, we call it the dew point, that huge volume of invisible vapor undergoes an epic transformation. It condenses into visible water droplets, releases an immense amount of latent heat, and boom, a cloud is born. On the other hand, if a mass of air is descending, the increasing pressure compresses and heats it up. And when air heats up, it literally evaporates those existing clouds right back into invisible gas, which leaves you with nothing but gorgeous, clear blue skies.
Okay, let's scale things up in Section 3, the aggressive cold front, or when cold air attacks.
So we're taking those foundational physics we just locked in and applying them to our first massive weather event. Take a look at this atmospheric collision. We've got a mass of dense cold air that's aggressively pushing into a region of buoyant warm air. Remember our golden rule of displacement? That dense cold air stays locked low to the ground and just violently undercuts the warm air. Notice the incredibly steep, blunt angle of that advancing blue mass. It's essentially acting like a giant atmospheric snowplow. It's forcefully and rapidly shoving the lighter warm air straight up into the higher altitudes, totally getting it out of the way.
Now, what's really interesting about this slide is exactly what happens when that warm air is shoved violently upward. Because the lifting from that steep, cold wedge is so incredibly abrupt, the condensation process kicks right into overdrive. It happens extremely fast, forming these massive, towering cumulonimbus clouds directly over the clash point. These specific cloud formations can rise vertically all the way up to 30,000 feet. To put that kind of energy into perspective, the immense latent heat released by condensation in just one of these major thunderheads can be equivalent to a small atomic bomb. No joke! That dramatic, explosive vertical buildup is precisely what unleashes the heavy downpours, the severe thunder, lightning, and those super intense squall lines.
So when you observe a cold front in reality, it operates with a very specific, recognizable fingerprint. Because of that abrupt snowplow-style lift we just talked about, the entire frontal system is relatively tightly packed into a footprint that's about 400 kilometers wide. And here is the absolutely crucial identifier to remember. Because of that steep wedge pushing forward, all of that explosive, heavy precipitation dumps out entirely behind the leading edge of the front as it sweeps over your location.
All right, let's play detective for a second and look at some real-world data to prove just how aggressive this shift really is. We all know British weather is famously polite and mild. Well, until it isn't. This is an actual graph tracking the air temperature in Wells, Somerset back on November 27, 2015. You can clearly see the steady, mild temperature all day long, hovering pretty comfortably right around 11 degrees Celsius. But then, right at 1700 hours, or 5 p.m., look at that sudden, steep plunge. The temperature literally drops off a cliff in a matter of minutes. That drastic visual line right there? That is the exact moment the dense, aggressive cold front bulldozed its way through the town, just violently resetting the local atmosphere.
Which brings us right to Section 4, the gradual warm front, a much slower takeover.
So here, the dynamics are completely flipped from what we just saw. Now we have a mass of warm air advancing toward a stationary or maybe a slower-moving mass of cold air. But think back to our rules. Warm air is highly buoyant. It lacks the kinetic energy and, honestly, just the sheer density to displace that heavy, cold air mass. It cannot act like our snowplow. Instead, the lighter warm air has absolutely no choice but to surrender to the physics of that cold barrier, and it just gently ramps up and slides slowly right over the top of it.
Let's move to convection and see how this builds across a much broader canvas. Because the lifting here is so gentle and gradual, it creates a completely different kind of weather system, one that is stretched incredibly thin over a massive 1,000-kilometer span. Just look at the sequence of clouds here from right to left. It essentially serves as a visual countdown for anyone watching from down on the ground. Way out ahead of the front, like miles and miles away, you'll first spot these wispy cirrus clouds high up in the stratosphere. That's going to be your early warning sign. Then, as the warm air continues to slowly march up the ramp, the cloud ceiling steadily lowers and thickens, transforming into altostratus, before finally bottoming out into thick, gray nimbostratus clouds right near the base of the ramp. And that's what brings those hours or even days of steady, persistent rain.
So, contrasting this with our cold front, the warm front has a vastly different operational footprint. Rather than some localized explosive event, it's this sprawling, elongated system stretching roughly 1,000 kilometers wide. And the absolute most vital difference here for forecasting is the rain. Because the warm air is gliding up and over that massive wedge of cold air, the precipitation from a warm front actually falls far ahead of the surface front itself. It just showers down continuously from that long, descending ceiling of stratus clouds we just looked at. All right, let's tie all these foundational blocks together in Section 5, comparing weather fronts head to head. And this brilliantly illustrates the extreme differences we've been unpacking today. When you put them side by side like this, the contrast is staggering. It's almost like analyzing two vastly different heavyweight fighters. On one side, you've got the cold front. It's a compact 400-kilometer footprint that delivers an abrupt, violent vertical punch. That creates towering storm clouds, with all the heavy rainfall trailing right behind its leading edge. Then, on the totally opposite side, you have the warm front, this massive, sprawling 1,000-kilometer gradual ramp. It creeps in slowly with a gentle lift, steadily soaking the earth with precipitation well ahead of its actual arrival. Two totally opposite atmospheric behaviors, entirely dictated by the simple physics of which type of air density is driving the movement.
Well, we've basically just handed you the ultimate cheat sheet for decoding the sky. You now intimately understand the physical rules of air density, the epic thermodynamics of how clouds are actually born, and the undeniable visual fingerprints of both cold and warm frontal systems. So I want to leave you with a bit of a challenge. Step outside today, take a deep breath, and really look up. Based on the specific visual countdown of clouds forming above you, and maybe the sudden or gradual shifts in temperature you feel against your skin, which front is moving in on your neighborhood right now? You've got the tools, keep your eyes on the skies, and keep exploring.